Hi everybody, it's Georgia Weidman here, and I am hard at work on the second edition of Penetration Testing, a hands-on introduction to hacking. Today we're going to look at the basics of exploit development, and I hope you guys all enjoy. Thank you for coming to We'll get started. You may have noticed that typically in this class I've just left the slides for you for reference. We haven't really looked at them too much, but in this case when we do exploit development there is a little bit of background I need to give you from the slides. There's plenty more slides for this section other than the ones we're going to look at, so by all means do take a look at them for your reference as you work through it. But let's take a look at a few little reference slides before we begin the hands-on portion of exploit development. So here on this first one we do have a somewhat dumbed down version of what a program looks like in memory. If you're familiar with this already, you'll notice some of the sections actually aren't there. Like there's a BSS section for non-initialized data that's not shown here in the picture, so it is not a complete picture. But what we're interested in particularly is the stack. That's where we're going to be doing our exploit development. We're going to stick to stack-based buffer overflows. There are certainly other kinds of memory corruption exploits, but we're just going to look at the basics of stack-based buffer overflows. So we are particularly interested in this section here. The stack, notice that the stack starts at high memory and grows towards lower memory. So you can think of it as kind of upside down. And if you forget that, when we actually look at memory, we'll be reminded of that. But high memory to low memory is the stack. Also, we need to know a little bit about our registers. You can think of registers as just a place to store data in the CPU for us to use it. And the registers are going to depend on your platform. If you're working with mobile phones and you have an ARM chip, your registers will be a bit different than what we see here. These are x86 registers, so EIP, ESP, EBP, so on and so forth. The E is for extended. It basically took the 16-bit registers and put an E on the front of them and made them extended for our 32-bit. And we actually really only have to, for this section, know the first three, EIP, ESP, and EBP. We will see an exercise that uses ESI, and if you continue in exploit development, you'll certainly end up using the others, but our most important ones are EIP, ESP, and EBP. EIP is our sort of holy grail for exploit development. EIP, the extended instruction pointer, it holds the memory address of the next instruction to be executed by the CPU. If our goal is to take control of the CPU and make it execute code on our behalf, having control of EIP seems like exactly what we should be after, and indeed it is. We have ESP and EBP, this extended stack pointer and extended base pointer. Those are the top and the bottom of the stack respectively, ESP pointing to the current stack frame's top or lowest memory address, because remember the stack is basically upside down, and EBP, the base, is the bottom or the highest memory address, so it keeps track of where we are in the stack, or in memory where our stack frame is. And again, there will be an exercise that uses ESI, and we'll see the other ones as we look at memory and look at what's in the registers, but really the only three that are very important to us and we need to know what they do are those top three, EIP, ESP, and EBP. So the stack, again, this is the one that we are looking at here. We're going to do stack-based buffer overflows. So it is a last in, first out, or I guess if we were going to get like technical with computer science jargon, I believe they say first in, last out, or last in, first out. I'm not sure. Whichever. You can think of it both ways. But you can just think of it as a stack of lunch trays. The last one that is put on by a cafeteria worker that's clean is the first one that is picked up by a patron. You have to kind of jumble things around if you want to do it any other way. And same way with the stack. If you want to take something off the stack, you only have one choice, it being the thing that's currently on the top. And likewise, if you want to put something onto the stack, you have to put it on at the top. You can't just insert it wherever you feel like. Certainly there are ways of addressing other parts of memory, but using the push and pop instructions, pushes something onto the stack, onto the top, and pops off the top of the stack. So again, I like the analogy of the lunch trays, but whatever makes you understand it well. Alright, so here is an example of a stack frame in memory. EBP is kind of like ridden up a little bit here. It should be down at the bottom. I'm not really sure how that happened. Then again, high memory at the bottom, low memory at the top, and ESP at the top, EBP at the bottom. But when things really get interesting is when we call another function. Typically, when you work with a program, it is going to have more than one function. If we do proper programming, we should definitely use lots of functions. We shouldn't just open main for a C program and then just write everything we're going to do in there. But even if we do, chances are we're going to call some built-in function of some kind, like to make it print to the screen, for instance. We would call something that's built into C, so we would be calling another function even if we don't make a second function ourselves. It would be fairly difficult to do anything useful without calling some function of some kind. So chances are we're going to have our main function call another function at some point. When that function finishes, and it may even call other ones, so you end up with lots of functions called. But when our function finishes, it needs to return back to main. So we need some way of keeping track of where it should return to. It shouldn't just start at the beginning of main again. It needs to pick up where it left off. So we need to store that somewhere, and that is the meat of what we're going to be doing. Is we're going to take that saved return address and we're going to manipulate it. So how this works in x86, again, it varies. Like ARM does it a little bit differently, but ultimately logically it comes out about the same. But there's really no like set way you have to do this. But for our x86, how this is done is when another function is called, before the stack frame for the new function is pushed onto the stack, well, is wound onto the stack. It's a little bit different than just push, 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 push. We can actually look at the assembly for that. It's basically it adds, or rather subtracts, because we want to move to lower memory, ESP, to make some new space. We'll see that. Getting a little ahead of myself. But anyways, before we do that, we actually save the return address. So we take the next instruction to be executed in main, or our currently executing function, and push it onto the stack. So we just save it there right on top of main stack frame. And then we create a stack frame for our new function on top of that. And then when the function finishes, its stack frame pops off and or is unwound, because again, it's not just popping off data. It's a little bit more complicated. We'll see that if we look at the assembly. But then we get rid of that stack frame, ESP and EBP. Then we'll need to move back into main stack frame from the function. And we take that saved return address that's right on top of main stack frame and we load it into EIP. So it returns as though we never left main at all. We just pick up right where we left off. So here's another little example here of what it looks like in memory. So we have main stack frame again. We have that return address, so that is the memory address to return to in main. So next instruction we want to execute when our function finishes. In this case, I've called our function function1. And we have ESP. While function 1 is executing, ESP will be at the lowest memory address or top of function 1 stack frame. EBP again kind of looks like it's gone up a little bit, but it is pointing at the bottom of the current stack frame, and it also has, in this case, the saved EBP from main. So we basically, at the bottom of function 1 stack frame, have our saved EBP. So what will happen when it finishes, we'll bring ESP back down to EBP. We'll get the saved EBP from main, move EBP there, and then, so basically we'll pop that off into EBP to restore EBP. So ESP, since we popped this off, will now be pointing here. That'll be our return address. we'll return to it, so we'll load that into EIP, so whatever is here, which should be our saved return address in main. Since we're doing exploit development, you might can imagine we might want to put something else there, get control of EIP. That is in fact exactly what we're going to do in this section. And then if we pop that off, then ESP will now be pointing back at the top of main. So we will have restored ESP and EBP. So again, we can see that with the assembly if we look at our assembly instructions. If you're not familiar with assembly, don't worry. No requirement for that. We're not really going to do too terribly much assembly in this class. Just the little bit we need in order to work through this. But that's just a general idea of how this works. So again, just a little bit of theory here. Just remember our registers EIP, ESP, and EBP, and kind of get an idea of what this looks like. When we actually look at a program, we'll see how this works. We'll see that it actually does follow the theory, which is nice. So with that, let's stop playing with slides and actually go ahead and look at it. Okay, we are in our Ubuntu 8.10 virtual machine. And I actually have the source code that we want already in here. So if we just go to Applications, Accessories, and then Terminal, and I can make this a little bit bigger. Zoom it in. You don't have to do this, of course, but just make it a little bit bigger, take up more screen space. We've spent a lot of time looking at a tiny terminal inside of Kali, after all. Alright, so we actually already have the source code in here if you're using my VM, which I've encouraged you to do so. Just download it, and we have it already set up. But if not, the source code is in the slides, and you can also just read it off the video, of course. So we have overflow test.c, and it is a simple C program with a little bit of a problem, as we will see. So it's pretty much as simple as a program can get. It doesn't do very much. So we have main. We learned about a little bit about C in an earlier section, I guess section 3. We learned a little bit of programming, including C. You don't really have to know much C for this class, but main will be called when the program starts, and it does take command line arguments. So the first thing that happens when we start main is it calls a function called function, and it passes the first command line argument, argv1. Argv0 is the name of the program itself, so argv1 is going to be the first argument supplied by the user at the command line. So we call a function. So if you remember our picture in our slides, we'll push that return address. So the next instruction to be executed, which one would assume would be the first assembly instruction of this printf, would be pushed onto the stack, and then we would create a stack frame for function, and it does take an argument. So inside of function, we create a character array called buffer, call it whatever you want, of course, and it's 5 characters long. So we will have 5 characters of space inside of the stack frame for function. We'll see we actually have a bit more wiggle room in there. There will be extra space for function to do its work, but we won't have unlimited space, certainly. And then we have string copy, or strcpy. So that is one of our bad functions in C. There's certainly not a rule that says you can't use this. It just, if we want to use string copy correctly, we would need to do some extra work on our own, and there are functions that do not have the same issues as string copy. Well, in particular, string copy doesn't do any bounds checking. String copy takes our source here and puts it into our destination, so it copies it byte by byte into our destination, and it doesn't care whether it fits or not. If we have, say, 5 characters to work with, we have no problem, or string copy has no problem copying 1,000 characters into those 5 characters. Well, that might not be such a bad thing, right? We would copy into the first one, the second one, the third one, the fourth one, the fifth one, and then we go back to the first one, and basically we just loop around, right? Well, no, that's not what happens at all. In fact, it just keeps writing down adjacent memory, so we will overwrite memory next to buffer. We could even write out of the stack frame, maybe even overwrite that return address and even part of main, and we could even write all the way to the bottom of the stack and make the program crash with an access violation. String copy does not care. So, again, we could use that properly. We could do bounds checking ourselves. We could just add in a little bit of code that checks to make sure our input is less than 5 characters. But in this case, the developer doesn't do that, so that is going to be our simple buffer overflow example. As you might have imagined, this was very similar to the way I was first taught, or I guess it wasn't how I was first taught, it was the first time it made sense to me, so thus I have kind of started teaching it the same way. And then we will, of course, move on to examples that are more real world, hopefully. People write programs that are a little more complicated than this one, but we will see some real programs in the rest of our exploit development. But this is just, pretty much as simple as it gets. We can get an idea of what's going on and also see a Linux example, since the rest of our examples will be in Windows. But our main problem here, again, is this string copy, strcpy. So after the string copy finishes, function finishes, and we return to main, which, if the return address is intact, should send us to this printf, which will print out to the screen executed normally. Notice there is a third function, overflowed, which just prints out execution hijack to the screen. But notice that under normal circumstances, overflowed is never called. We start with main calls function just returns, and then we printf executed normally, and that's the end. Overflowed never gets called, so it's like debugging code that just got left there or something. So you can imagine our goal is going to be to call overflowed. So that's exactly what we're going to try and do. Again, if you're using my VM, you don't have to worry about doing this. There's already a compiled version of this program. But if you are not, for some reason, we do need to compile it. So we want to do gcc, like a new compiler. And we can put debug symbols in there with -g. And let's see, we need to put a flag in there, fno-stack-protector. What that's going to do is turn off a stack protector, or a canary as it's called. We're not going to cover the canary in this class. If you continue with exploit development, do an exploit development class, for instance, you probably will work with canaries, but we're going to start with the basics here, so we just want to turn it off. And -o for the output, I'll just call mine overflow test. It's just going to overwrite the one that's already there. And the input file is overflow test.c. The main thing we need to do is just fno stack protector. The debugging symbols we don't really need, and if you change the output to something else, it will give it that name. And if you don't put the -o, it will call it a.out. A.out is fine. We don't really care what it's called. It does throw a warning. Basically, it says that main is not an integer. I made it a void. Whatever. Still compiled. That's not the source of our buffer overflow. That's just it complaining about things it doesn't really need to complain about. Alright, so now that it's compiled, we can go ahead and run it. So overflow test from our current directory. And remember, it does want user input. And since we know the source code, we know that it wants basically 4 characters, because string ends with a null byte. So someone pointed this out to me in a class a few years ago. So it's just like, oh, it can be 5 characters. And you'll see that it can be, but technically we will have actually overflowed the buffer. I say that with air quotes that you can't see, because if it doesn't actually cause a crash or anything, it doesn't particularly matter. But technically, if we give it 5 characters, we have overflowed our variable at least by 1 character, because that null byte at the end will actually make us write to adjacent memory. So let's stick with 4 characters to be precise. So overflow test with 4 uppercase A's, and it prints out executed normally as expected from the source code. But what happens if we say overflow test, and then just, be heavy-handed about it. It doesn't particularly matter how many we put in at this point. Just held down the big A for a while. We do not get executed normally. We get something called a segmentation fault, so we have made the program crash. So it clearly has some sort of, if not exploitable vulnerability, then at least, it's not very good at dealing with unexpected input, which is generally a good place to start looking for vulnerabilities that can be exploited. So, naturally, as exploit researchers, we would want to know more information about what exactly is going on here. So, what we're going to use is a debugger. When we move over to Windows, we'll use a more graphical debugger called Immunity Debugger, but here in Linux, we're going to use a command line tool called the GNU Debugger, or GDB. So we use GDB and tell it to open overflow test. We get, some stuff written out to the screen. Says this is the GNU Debugger, hooray. Alright, so if you don't know anything about the GNU Debugger, don't worry. You can read manuals about it. I've never found the manuals to be very beginner friendly, but there's a good tutorial series at SecurityTube that I would recommend, or, just playing with it. But for this class, we don't really need much GNU Debugger information. Anything we are going to do, I'll show you. And we're certainly not going to cover all the things that it can do. We're just going to look at a basic example here. Debuggers aren't made specifically for exploit research. They are primarily made so developers can debug their programs, see what's going on, but they are widely used by exploit developers to try and build exploits, as we will do. Alright, so let's go ahead and take a look at the source code. Since the source code is in the same folder, we can do that. We can actually list out our source code. That's going to make life a little bit easier for us. Naturally, since C is compiled, we will not always have our source code, so we may have to work a little bit harder. When we move to our Windows examples, we won't have source code, so we'll have to work entirely with what's in memory. But here we do have our source code, so if we do list and say 1, 16, there are 16 lines, so that's going to list out 1 through 16, as we see here. So what we're going to want to do is actually set some breakpoints, which are breakpoints, as the name might imply, is they are going to cause the program to pause or break when we hit them. We don't have to set them on a line like we are here. We're just going to put in line numbers, but you can also have them set on a function or a memory address. Lots of different ways to set them. But again, we'll start with something simple here. And I want to set 3 breakpoints. I'm going to start here in main. I want to take a look at the state of memory right before we call function. Remember, function is where the bad stuff is going to happen. We have that string copy function that, since we have the source code, we can probably tell that that is the source of our problems, why we're getting that segmentation fault. So let's go ahead and set a breakpoint here right before the call to function. So if we set our breakpoint on line 14, that will pause execution right before our function is called, so right before that line is executed. So break 14, so we just tell it to break on line 14. Sets breakpoint 1 at the memory address of line 14. And then if we do a break in function, so then we will be in function. And I want to do a breakpoint right before string copy executes. Again, string copy is the source of our trouble, so we're really interested in what happens there. So for reference, we'll basically get a snapshot of memory right before the string copy happens with our break 10. And then right after, we'll just break at line 11. So right before function returns, we'll see what happens during string copy. So we'll see the state of memory after the string copy has occurred. So finally, our third breakpoint will be break at line 11. So 3 breakpoints. Again, break 14, break 10, and break 11. So break in main right before a function is called for reference. Break right before the string copy, again for reference, to see what memory looks like before the vulnerable function. And then finally, right after the vulnerable function at line 11. Alright, so now we've got our breakpoints, and let's go ahead and run this. So to do that, we do say run, and we give it any input that we need. So again, let's start with 4 A's. Again, 4 bytes here. And go ahead and hit enter. That will have it start. So it'll either run the program till it finishes or it hits a breakpoint. We hit our first breakpoint, which is the breakpoint 1 at line 14, so right before the call to function. So now that we're at a breakpoint, we can examine our memory. So there's lots of different ways you can do examine. Like, it has lots of different ways you can format the output and say how much data you want. So we can say help X. So that's one way of getting data. Like most programs, we can say help and it'll give us some help information. So he tells us more details about the examine command. So basically we say X / the format we want and then the address we want, which we can give it like a register name or a memory address. And so what we're going to do, and this is certainly not the only way to do this, but this is just the way I was taught, I guess, and that's what has been useful for me. So I'm going to examine / so it's X / and then we tell it the format we want, which I want hexadecimal. We're going to see lots of hexadecimal in exploit development, so you'll have to get used to reading some hexadecimal if you continue in exploit development. And I'm going to tell it I want words, so W. And I'm going to tell it I want, how about 16 words? That will probably be more than we need. So we'll see how many we need to get to the bottom of main stack frame, but I'm just going to tell it I want to examine 16 hexadecimal words from $ESP. So that, remember, ESP is the top or lowest memory address of our current stack frame. We're currently in main, so we paused right before we called function. So this should show us main stack frame and probably a little more depending on how big main is. We did ask it for 16 words. That's probably more than we need. Alright, so how we can read this is these are the memory addresses over here and here's the data in them. So this is in hexadecimal, so there's going to be base 16, so 4 bytes here, 8, 12, 16, and then we wrap back around, so we go up to 9, and then A, B, C, D, E, F, and then loop back around to 0. Alright, so this would be the memory location of ESP, so the top of main, and this would be whatever is in there. So to get a reference of where main ends, we would need to examine, we just need one hexadecimal word here from EBP, which again is the bottom or highest memory address. So notice that we do go to higher memory addresses as we go down the stack, so C, D, E, F, so going higher there. So it says EBP is at C8, so indeed 16 hexadecimal words is way more than we need. It looks like this is main stack frame, so not much to it at all. In fact, only 12 bytes. Then again, main doesn't do very much, so that's not entirely surprising. Alright, so that again is just a reference. Nothing particularly interesting happens in main, at least from an exploit development perspective. So to move on and let the program continue, we say continue, so that will again either go to the end of the program or the next breakpoint. So we hit breakpoint 2. We're now inside a function right before the string copy. So we can hit the up arrow to get our old instructions back. So if I just go up to my examine 16 hexadecimal words from ESP, now that we're in function, ESP will now be pointing at the top of function stack frame, which should have been put on top of main stack frame. So we should have lower memory addresses, because again, stack moves up towards lower memory addresses, so we should see B0, A0 over here. That's indeed exactly what we see, so here's A0 at the end here, and we can again get EBP, which again should be pointing at now the bottom of function stack frame. So since it's at B8, so this is part of function stack frame as well as this here. So a little bit bigger stack frame here. 5 of those bytes are going to be for buffer. We don't know which 5 those are yet, but we will see that presumably after the string copy. We should see our A's show up, and we should be able to tell when we hit our next breakpoint. So remember, if we look up here, so starting at our C0 is where main is. So this is main, it's stack frame, and this is function. So what's this? So if we remember our picture, when I showed you the slides in one of the previous videos, we have main stack frame. On top of main stack frame, we should have the return address, so the memory address of the next instruction to be executed when function returns and we go back to main. And then we should have function stack frame. So this should probably be, if in fact my theory is correct, this should be our saved return address. So 08048443 should be a memory address in main that should be our next instruction to be executed. So we can disassemble a function. So if I say disassemble and then main, tell it to disassemble main. Here's some assembly. You may not be too familiar with assembly, and I particularly, this is in AT&T format, and I prefer Intel format, so even though I do know a fair amount of assembly, it's rather hard for me to read these because the formatting is a bit different than what I'm used to. We can change that if we want to. We could do set disassembly dash flavor. You don't need to do this if you don't want to. I can't spell disassembly apparently. No, I can't. Alright, so set 1s here. Disassembly flavor. My spelling is getting worse by the minute. Intel. I misspelled it again. There's an E there. There, finally, no error. So, set disassembly dash flavor to Intel. Again, you don't have to do that. I just prefer Intel format, so this format is much easier for me to read. But luckily, it doesn't particularly matter if we know assembly, because we're interested in what is the call to function, even if we can't read assembly call and then function. That even if we can't read assembly, that pretty much jumps out of it that is indeed the call to function. So our next instruction to be executed is probably this one. I mean, that would make logical sense. So 08048443, which I've run off the page because I can't spell disassembly. So if I go back and examine again from ESP, so we have 08048443 is our saved return address. So that should be the memory address of the next instruction to be executed. Sure enough, that's exactly what the next assembly instruction in main after the call to function is. So it looks like everything is exactly like my picture said it would be. How interesting. Alright, so let's go ahead and continue again. So let's let that string copy execute so we can see what happens in memory. So we have this as a reference. So this again is function stack frame now. Let's see what changes when we let string copy run. So if we continue, we hit our third breakpoint right before function exits at line 11, so after the string copy. Again, let's examine our memory. So, a quick reference here. It looks like a few things have changed, but in particular, 41 is hexadecimal for an uppercase A. You can look at a man page for ASCII, and it will actually show you all of this, or you could go to like ASCIItable.com if you need to reference what is what. I mean, certainly I can't expect anyone, since I don't even, to know all of the ASCII table, but, as you spend more time with it, like 41 you'll probably remember, because for whatever reason, typically people just start overflowing buffers with bunches of large A's. So you see lots of 41s in memory, but, if you need to check what it correlates to you can always look at an ASCII table. Again, there's man ASCII, or I like ASCIItable.com if you like something a little bit more graphical. So we have 41 here as the first character here, and we have 41, 41, 41, and then a null, which again terminates a string. So it looks like that's where our 4 A's showed up, so this should be where that buffer variable is, and it did indeed fit nicely inside of our stack frame. So again, the return address is all the way over here, so you can kind of start to see an idea of what we're going to try and do, since we want to get control of that saved return address. If we, instead of putting 4 A's in, we just kept putting A's in, and that string copy would allow us to overwrite adjacent memory, and would eventually could overwrite as much as we liked, really. But for now, it did all fit nicely. Our only question is, why is this one off by itself, and why is it like turned around? It's like the null that's the end seems to be byte number 2, if this is byte 1 and then 2. So it looks like things are a bit backwards, which when I was first starting exploit development, this really baffled me and made me waste a lot of time. So we will see exactly what's going on here, and if I teach you one thing about exploit development, you will never make the same mistakes I did. So we'll see that in our next video. But for now, let's just go ahead and continue and let the program finish. It does print out executed normally, and the program exits. So since we only used 4 characters as our input here, everything works fine. And again, naturally, the next thing we're going to do is try and overflow it. Alright, so now what we want to do is actually try and exploit this. In our last run, we just gave it 4 A's as the input, and they showed up in memory, and they seem to be, well, backwards. And here's our return address right here. If we recall, that is the next instruction in main to be executed, so we want to overwrite that return address. So in this case, we could really just count how many bytes we need. As we'll see with later exercises, that's not always going to be the case. But we put in 4 A's before, so here's 5 with the null, 6, 7, 8, 9. So it looks like we need 9 bytes of padding, and then naturally 4 bytes to overwrite the return address. Hex 2 digits is a byte, so we want 9 bytes of padding, and then 4 bytes to overwrite the return address. Again, in this case, we can just count. So let's run this again. Again, that's run, and then we can put in like 9 A's and some B's, but eventually we're going to have to use scripting anyways when we start using a return address that's made of hex instead of just some B's. So let's go ahead and do that. So if we do a $, and then open parentheses, we can run a script here. So we could do Python or Perl or any scripting language that this Ubuntu system knows. So we're going to use Python for the rest of our exercises, so why don't we use Python here. So let's do Python-C to tell it to run a command. Open single quotes, and I want to print double quotes A times 9 plus double quotes around B times 4, so that's A. So our 41s times 9 for our padding, and then B, which will be the next number in hex, which is 42. Again, you can look at an ASCII chart for that if you are not familiar with these. And so 4B's is going to be overwriting our return address here. So this should make the program crash, so we want to close up our command. So we need a single quote here at the end, and then close parentheses. So this is going to tell it execute this script, and whatever the output is going to be our argument. So in this case, we could have just typed out the A's, but again, when we want to turn this into an actual hexadecimal address, really the only way to do it is using scripting. If we just like type in 08048443, it will take that as 8 different 1-byte characters instead of hexadecimal. So let's go ahead and run this. Our breakpoints are still going to be set. We can delete them, or if we restart GDB, they'll go away, but otherwise they will stay, and we want them for now, so just leave them. Let's go ahead and run it. Alright, so we hit our first breakpoint. Again, that is in main, so before we call function. So again, we can examine an x slash, let's see, I believe it was 12 bytes. Well, let's just leave it and say 16 again. We'll just do too many. So 16 hexadecimal words from ESP. Again, that is the top of main stack frame. Notice that we have moved up the stack some, so our last digits are 20 here, whereas previously in main, I believe we were at C0. If this is the return address, and this is the top of main. So we have moved up the stack some. That is to be expected. One of the things that makes a difference about where you end up in the stack is going to be the length of the argument. So since we did change the length of the argument, we should expect to move somewhat. Shouldn't change our next round since we've got our 13 character input, so we should expect to be in the same place next time. But that's nothing to worry about. What we really care about is our offsets, just to make sure that our 9A's plus 4B's will overwrite that return address. So as long as our stack frames are the same length and our data is going in the same place inside the stack frame, our addresses don't particularly matter. Okay, so let's examine, just to make sure that our stack frame is the same size, let's just examine one hexadecimal word from EBP, our bottom. Sure enough, this is still main stack frame, so still rather short, 12 bytes. Alright, so let's go ahead and continue. Move us into function, where we hit our second breakpoint. We'll use the up arrow to grab previous commands. So I will again look at ESP. And now we have moved up some more. Notice what hasn't changed here is we still have the return address 08048443. We can again do a disassemble main to see that. So here is our call to function. And that returns the next address to be executed, 08048443. So that should be our return address. If we examine from EBP again, remember ESP and EBP are now inside of function stack frame. So sure enough, same size stack frame here, return address, and then main here. Alright, so let's continue and hit the string copy, let that execute. We hit our third breakpoint right after the string copy. Now if we take a look at our stack, we have our 41 over here by itself again, all 41s here, those are our big A's. Big A's here, and then where the return address was, we indeed have 42, 42, 42, 42 for uppercase B's. So our offsets are correct, and we have managed to overwrite that return address. So what's going to happen now is that the program will just continue on as it blindly does. So we'll get rid of the stack frame here, will be wound off the stack, and it will just automatically try and load this address. So it will load that address into EIP. We can always do info registers. I didn't mention that, but we can do info registers here and see all of our registers. So again, our 42, 42, 42, 42 will be loaded into EIP. Whatever is at that address, if anything, will be executed next after function returns. If 42, 42, 42, 42 is not that mapped to an executable portion of memory, then we will get a segmentation fault and it will crash. That is most likely what's going to happen here, though there's no rule that says 42, 42, 42, 42 cannot be a valid memory address. You may find cases where it will be. So we shouldn't just blindly assume the program's going to crash, but often it will. Let's go ahead and continue. And this time we do not get executed normally printed out to the screen. We get a segmentation fault. So it's trying to execute 42, 42, 42, 42, and that's not mapped to anywhere, so there's no instruction there to be executed, so the program just throws up its hands and crashes. So we've caused a denial of service condition, but surely we can do better, right? So let's see indeed, if we can. Okay, so now we want to see if we can turn this into some sort of exploit, execute some code that wasn't intended by the developer. So again, if we list out our source code with the list command, remember that we have that third function, overflow, that never gets called. You can think of that as some debugging code that just got left in. As we'll see later when we do our Windows examples, we won't always have this luxury. One, we won't have the source code, and two, there's nothing to say that there's going to be code lying around that we necessarily want to execute. We'll instead use some shellcode, so like the Metasploit payload system, where we say we want Windows Meterpreter reverse TCP as our payload, then magically when we run, say, MSO8067, Metasploit just magically puts the payload in the right place and it executes, and we get our Meterpreter reverse shell. So we'll do that manually. We'll create some shellcode and drop it into our exploit in the correct place, and we'll learn all about that in our next exercise when we move over to Windows. But for now, again, we'll start with the basics, and all I want to do here is get execution hijacked printed out to the screen. Not as exciting as a reverse shell, of course, but it will be technically an exploit. So that's going to be what we want to do. So I need to know where overflowed is. Just because it isn't called doesn't mean it's not in memory. So if we disassemble overflowed, the first memory address of overflowed is here. See, our prologue here. So we push EBP. Remember EBP, to save the EBP from, say, main or whatever the current function is, pushed onto the stack. So that is the bottom of the new stack frame, and then we move ESP into EBP, and then subtract, in this case, 8 in hex from ESP. So again, moves ESP up. So basically we have ESP moved up, and then we have ESP adding some more space. So kind of beyond the scope of what we're doing here, but kind of how a new stack frame is made. If you're interested in exploit development, I certainly encourage you to learn some assembly and figure out how these programs work. It is going to vary a little bit from platform to platform, again, how this is implemented, but they pretty much all end up doing kind of the same thing. In the end, it's just how they implement it is a little bit different based on the platform. Alright, so let's go ahead and do what we're going to do. So we want to grab this address here, and instead of our 4 B's that just make it crash, we want to put that address of the first instruction in overflowed into our saved return address. So instead of going back to main, we'll be redirected to the beginning of overflowed, and it'll make execution hijacked execute. Alright, so let's do that. Again, we can go up to our little Python script here, and we tell it to run. We want to take out our b times 4. We can leave our a times 9 in. Remember, that's just padding to get to the offset of the return address. We have b times 4. So we want \x to tell Python that this is going to be a hexadecimal address. So we want 08 \x 04 \x 83 \x f4, and then close our double quotes and close our single quotes. So now we have a times 9 plus, in hexadecimal, the return address is going to be the first address in overflowed. So we should be redirected to overflowed if we've done everything correctly. Since the program crashed, it says it's already started, so do we want to start from the beginning? We can say yes with a Y. We hit our first breakpoint. Again, that's in main. So we can look at ESP and EBP. Again, 12 bytes long, no change there. Go ahead and continue to the second breakpoint. And again, Same size here for functions stack frame. And we have our 08048443 here. That's our return address that hopefully string copy will overwrite correctly for us. So let's go ahead and continue to the third breakpoint. Alright, so we have our 41s, our 9As, and this should be our return address. We disassemble overflowed. We should have 080483F4. And we look at the command, that's what we told it, 080483F4. But if we actually look at our return address here, it's F4830408. What has gone wrong here? Well, it's not exactly backwards, but if you remember that in hexadecimal, 2 characters make up a byte, it looks like we're backwards byte by byte. So F4 is first, and it should be at the end. 83 is second. 04, and then 08. So again, byte by byte, it's backwards. If we remember back a couple videos ago, we had 141 off by itself. Well, we still do. It looks like it's the beginning here, and then we have other parts of our stack frame that have not been overwritten here. Then we had 41, 41, 41, 41, and then we had a null byte again at the beginning. So that was a little bit confusing, right? Why that happened. It again looked like things were backwards, and indeed, seeing this, it looks like there is really something that is turning things backwards byte by byte. So when I first started exploit development, I had no idea what this was. I had not paid enough attention in operating systems class, no doubt, and I was very confused, and I spent lots of time trying to figure out why my exploit wasn't working. So if you learn one thing about exploit development, just learn this. This is something called Endianness. So this comes from a book called Gulliver's Travels. Gulliver, on one of his travels, ends up in a place called Lilliput that has a war going on with one of their neighbors over which side of the egg you should crack. So people who say you should crack the big end of the egg are big Indians, and people who say you should crack the little end are little Indians. So we have kind of the same thing in computer science. So that is Endianness, spelled like this. So Endianness. So not like people from India or Native Americans, so with an E. So if you're not familiar with Endianness, I encourage you to Google it. There are white papers and Wikipedia and such. There are platforms that use Big Indian as well as platforms that use Little Indian. Never really come up with a good answer as to why one is better than the other. Everything I read in the white papers pretty much say it makes really no difference in terms of like speed and things that should matter to people who are designing chips. So as far as I can tell, it's really just a preference of the chip developers. But our Intel architecture here is Little Indian. Chances are most of the chips you'll end up working with are going to be Little Indian, but it may be big. You will, no doubt, if you try every platform you can get your hands on, run into something that is Big Indian where you will not have to flip the bytes around. But just as a good rule of thumb, I just remember chances are it's Little Indian. So all I need to do to take into account my Little Indianness is just flip our bytes around. So take the least significant byte and put it first, and most significant byte will be last. So again, just flip it around byte by byte. You don't really need to know the details of how and why this makes a difference to the chip. But again, if you're interested, I encourage you to look up Endianness. And if you can come up with a good reason why one is better than the other, then I can stop saying in my videos that it doesn't really make a difference. Alright, so easy to fix here. Let's go back to our run command and flip these around. Though we can just say continue, and it does indeed crash. So instead of going to 080483F4, it tries to go to F4830408. So again, it's backwards, and that's not mapped to overflowed, or in fact, it's not mapped to anywhere. So we again get our segmentation fault. So again, let's go up to our run command, and we just want to flip these bytes around. Not too hard to do. We want F4 first, so least significant byte first. 830408. So this should work out nicely for us. So let's go ahead and run it. Again, we say yes to restart. And just continue through our first two breakpoints. We've pretty much got the drift of what's going on there. Hit our third breakpoint. Take a look at our memory. We have our 41s again, same place. And now our return address 080483F4. Taking into account Endianness did indeed fix our problem. So just try and remember your Endianness, and if things seem to be backwards, oh, I forgot Endianness, easy for us to fix. So you won't spend lots of time wondering what's going on like I did. So just a good rule of thumb. Alright, so now if we continue, it does print out execution hijack to the screen. One thing to note though, after it prints out execution hijacked, we do receive the segmentation fault. It does crash. An ideal way to fix this would be if we had shellcode instead of just some function, we would use an exit routine to make the program exit gracefully. Whereas here we don't have any exit routine, so after execution hijacked is printed out, overflow tries to finish and return back to the previous function, which since we kind of screwed with things, it's just not going to work. So this is supposed to be the return address here, so it thinks it's returning back to main or to some function, but instead we jump over to overflowed, so we never save a return address. So again, this stack frame is going to be gone, this will be gone, that's what will load. So it naturally thinks, the program is just designed, or rather the platform is designed to think that this will be our return address, since it will be the top of the stack after overflowed removes its stack frame. So that should be the saved return address, but unfortunately it's just data from main plus should have a null byte at the end here. So it's like, okay, whatever. But the program just, blindly tries to execute that. It's like, okay, well, you're the top of the stack, you're the saved return address, so you must be this save return pointer, and sure enough, it's not mapped to anywhere, and we get a segmentation fault. We can kind of fix this in the short term if we want to. We could take our original return address and put it here. So that would redirect us into main, but we have destroyed main stack frame, so if you put the original return address here, of course in little Endian format, then you can see it will also print executed normally to the screen, but then again it will crash, it can't exit properly, so we've pretty much destroyed the program at this point, but we did make it execute commands on our behalf. Again, in this case it just says execution hijacked, not too exciting, but we will in our subsequent examples use some shellcode. We'll let MSF Venom generate it for us, and then we'll get a nice, more sophisticated working exploit. But again, I learned it this way. This was the first example that really made sense to me, so I do something similar. It wasn't the exact same program, but it was a similar notion of, well, we are supposed to go here, but instead we take control of the CPU and go here instead. So we get control of where we want to send stuff, and then we send it somewhere else. So, again, pretty simple example here, but I think a necessary building block for beginners to look at the other exploit development examples will do. So let's go ahead and do that. Let's switch over to Windows and look at a little more sophisticated example. Alright, let's work on our next example. This time it is going to be a network-based exploit. In our previous example, it was all local. There will be certainly local exploits if you continue in exploit development. We saw some client-side attacks when we did that section, something like Adobe Reader, music player, anything that is local privilege escalation, for instance. But these next few are going to be network-based, so like many of the exploits we used in this class, we will have something listening on the port that's vulnerable, and we will attack it over the network. So for this example, we're going to use Windows XP, and we'll have Kali as our attacker. So on XP, we actually need to make a simple change. So if we open up the XAMPP control panel, we currently have FileZilla FTP running. Let's go ahead and stop that. Open up that port 21 TCP for another FTP server. You can close that up. And now if we go to the war FTP folder, we have all our war FTP programs here. So we actually want this yellow thing that looks like part of a state, really. This says FTP, so this is the war FTPD daemon. Let's open that up. And we can click OK through the opening banner that says who wrote it. And we need to put this online. By default, it is offline, as it says down here. So we would want to hit this lightning bolt up here. So I'll go online. And sure enough, it's online, and it's listening on the IP address of XP on port 21. So what we want to do now, before we start exploiting it, is we want to, like we did with GDB in the previous example, we want to hook it up to a debugger. There are many different options, really, for debuggers in Windows. Probably the most powerful would be WinDebug or WinDBG, which is a little bit, I think, more complicated than the one we're going to use. We're going to use one that I like to use called Immunity Debugger. It is pretty powerful. It has its limitations, like we can't do any kernel debugging with it, so in that case we'd have to use WinDebug, but I like to use Immunity Debugger when I have the option, and I think it's especially nice for beginners. So let's grab Immunity Debugger. It is this red, black, and green 3-leaf clover. And it opens up this graphical window for us. And so we want to attach to war FTP, so we go to File and Attach. We have a list of our processes. So we want war FTP. It's easy to spot because it's listening on TCP port 21. So if we look at the listening column, we can see port 21 here. We can click Attach. And we see that it attaches to the process and it's paused at DBG breakpoint. So basically it pauses when the debugger attaches. So what we want to do is click the play button up here to tell it to continue so the program will run so we can attack it. So now it's running. You can see that down here at the bottom right. Just going to make this CPU window bigger. So I'm just maximized it. I can make the font bigger. I typically don't, because if I make it bigger then it starts to like run off the screen. But you can make it bigger if you go to Options and Appearance. If you go to Fonts, you can make it bigger. It's not much bigger really, but you can make it bigger. Like if I'm teaching in front of a class, I typically do. But you know, you can make yours bigger so you can see it on your screen since this is recorded. But you know, you do have that option if you want to teach this yourself. It's kind of worth knowing because it looks microscopic on a projector. Alright, so this is running and we are hooked up to the debugger. Again, I made this CPU window maximized, so I have 4 panes here. Go to different windows. You can go to View, up next to File, and we will see some of these other views as we work through these examples. Some of them we won't see. With the CPU window is our default here. So we have our CPU here at the top left. Top right we'll have our registers. We have EAX, ECX, EDX, EIP. And we have our dump here at the bottom left, and bottom right we have our stack. Alright, so naturally we need some sort of exploit here for war FTP. So if we pop back over to Kali, if you look at the materials that are included with the course, I do have some exploit skeletons. We don't have to know much Python for this class. We did, of course, cover a bit of Python previously in our 3rd module. But I gave you the exploit skeleton, so this is just war ftp skell.py, and as you can see I copied it onto Kali's desktop, so you can download that file. It is included with the course. It just has the basic Python code, so we can focus on trying to build our exploit string. If I change directories to desktop and do a cat war ftpscale.py, first we have user bin Python, so it tells it to execute in Python interpreter. We import a socket, so that's going to be a Python library. That, as the name implies, sets up a network socket. We see buffer, so a variable named buffer equals a times 1100. S equals socket.socket, blah blah blah. So that's just how you set up a socket in Python. If you're not familiar with it, you could basically just Google it, how to set up structures like this in different programming languages. Is not really something you need to memorize in your head. You can always look it up, of course. So that's probably what I did when I first wrote this. And I tell it to connect, so s.connect. We are going to have to change this IP address to the IP address of your XP machine. So I will look up mine, of course, and yours may be different. And port 21, that is the TCP port for FTP. We print out a response if we receive one, then we send the correct syntax for giving the username to an FTP server, so it's just user space, whatever our username is, and then hit enter, so /r/n or /r/n. And our username is buffer. Remember, buffer is a times 1100. So we're basically giving it a really long username, probably much longer than the developers expected, because who would want to type in a username that long? But that's generally how exploit development goes. We give it unexpected input that the developer didn't know was coming, and possibly make the program do something strange. Again, we print a response if we receive one, and then just to finish the login, we do pass space and then the password. And obviously there is no user called a times 1100, so we just need some password, so I just gave it password. All uppercase is the password. And then we close the socket, so we just need to make it take our username and password and try and process it in order to get the vulnerability to trigger. So if you copy this onto the desktop, you may have to do a chmod +x, of course, to make it executable. And we do need to change that IP address. So I'm going to use nano. And what is my IP address? WarFTP actually told me 192.168.1.76. Change yours to meet your environment accordingly. That is the only change we need to make right off the bat. We'll leave that a times 1100 as our attack string, as our long username. We will make changes to that as we work through this example. Again, we've got our simple source code here, so we don't have to worry about the nitty-gritty of the Python code. I encourage you to learn at least one programming language well. Python is used a lot in information security. Ruby is also used a lot. Not so much Perl. I used to write in Perl all the time, but not many people use it anymore. C is always a good one to know, but I encourage you to know a bit of lots of languages and at least a lot of one language, but you don't really have to for exploit development, honestly. Just basics is probably enough. Alright, so let's go ahead and run this. Just /warftpscale.py. We don't have to give it any arguments. We've hard-coded our IP address in. We could instead take that as an argument if we wanted to. So we get printed out to the screen our welcome banner. It says please enter your username, which we do. And then it says username okay, need password, and if we recall, we do send over the password and then close the socket. So everything worked as expected from this side, but of course what's really interesting is hopefully what happened over here. So here we have our WarFTP and immunity debugger where we left it. When we left it, it was running. Now if we look down here at the bottom right, it is paused. It says we got an access violation while executing 41, 41, 41, 41. Well, do we remember what 41 is in hex? We do a man ASCII. That'll tell us. So hexadecimal 41, if we've forgotten, is going to be over here in the second column. 41, big A, just like in our previous example. So we sent it 1,100 big A's. So it looks like those big A's, much like our previous example, they overwrite that saved return address. We don't know what our functions are called or anything at this point. We don't have any source code for this, but chances are we overwrote some saved return address, and when the function popped off and we tried to load that saved return address, it was overwritten by some A's, and 41, 41, 41, 41 is not mapped to the process. Again, it could be. There's no hard and fast rule that says 41, 41, 41, 41 will always make it crash. If you continue in exploit development, no doubt you will find examples where it doesn't crash. But for now, it did in this example, so it tried to execute at that memory address and it crashed. We also see there seems to be a lot of 41s on our stack. And looks like we've got some 41s in some of our registers too. Looks like ESP, EBP, and EDI all have some A's in there. So in our previous example, we could just look at our debugger output and we could count, oh, we need 9 A's to get to our return address, which is 4 bytes long, so we could do A times 9 plus B times 4. We don't really have that luxury here. We don't know what A's are which. We have 1,100 of them to begin with, and we don't necessarily know that what's showing up in memory necessarily starts at A number 1. It might not. We don't really know how it's being processed. There's some sort of login functionality that's trying to check our username and password, and it crashes at some point here, so we don't really know what's going on. We could do some reverse engineering to try and figure it out, but that's more advanced. So we need some way to figure out which 4 A's those are. So traditionally, what one would do, if we go to, just open up Notepad here so I can show it to you. Traditionally, what one would do would be break it into like A times 500 plus B times, well, 550. This is 1,100. 550 and B times 550. Restart it, send this exploit string, and if it's overwritten with 41, 41, 41, 41, we know it's in the first half, and if it's overwritten with 42, 42, 42, 42, we know it's in the second half. So say it's in the first half, then we would restart and do A times 225 plus B times 225, and then C times 550, because we know that the second part is not where it is. So then, we'd run it again, and if it was A's, we'd know it was in the first half, and if it was B's, we'd know it's in the second half, and then say it's in the first half again, we'd split that in half. So you'd slowly but surely, with lots of tedious work, narrow it down to the exact 4 bytes, which was tedious and boring, and I can't believe people did that for as long as they did. Naturally, we have a better way of doing this, so that's what we will do in the next video, is try and solve where exactly our saved return pointer overwrite happens in the attack string, as well as where exactly we have control of these registers, because they will come in handy as well. In our previous example with Linux, we just jumped to another function, but I mentioned that we're going to use shellcode here that we're going to generate with MSF Venom, the more traditional way of doing exploit development. So we'll need somewhere to put it, and it looks like controlling those registers might be a good place to start. Okay, so now we need to figure out which of the 1,100 characters are overwriting the save return pointer and thus causing this crash in EIP. So what we want to do is create a cyclic pattern, and we're going to do this in Immunity Debugger. And we do our commands down here at this white part at the bottom, but that's kind of small, so I will put them in Notepad first so we can see them a little bit better. And we do, of course, need to restart WarFTP. It's currently crashed. Some programs we can do this inside of the debugger. That will not always be the case. Sometimes you'll have to detach and restart it. But with this one, we can go to debug and then restart. Say yes. And seems to have restarted nicely. If you do have any problem with it, it may, in a few cases, I'm not really sure what it is that does it, because I can give people the same VM and most people don't get the error, but then a couple of people do. But if you do get an error and it says like unknown database format or unknown username format or something like that, it'll just put up an alert window that says that. If you go into the WarFTP folder, there will be a file ftpdaemon.dat, and if you do get that error, just delete it before you restart. It just deletes the database. And if you don't get it, then you don't have to do that. You can just restart like we did. But if you do get that error, and if we do get this error in a later video, then I will show deleting it. But just in case you get it, you can just delete that file and everything should be fine. So it does pause when you restart. So we see pause down here, so we can click play. And where did my WarFTP go? It says it's running, but it's not there. Alright, so let's just say restart again. And hit play. There we go. Unknown file format or user database. Cool, I got to see it. Alright, so we got to say OK here, and let's delete that ftpdaemon.dat. Again, you probably won't get this, but luckily for the state of the video I did, so you can see how to get rid of it. So just delete the .dat file, ftpdaemon, and now go to restart, and it should restart fine. Cool. Click OK, click the lightning bolt so it's running, and we're still attached to it in the debugger. So we should be good to go. Alright, now we need our command to create our pattern. So we're going to use a add-on called Mona, and it is added on to Immunity. It's not in there by default. You can just download it and add it to Mona. We did that, or add it to Immunity rather. Add Mona to Immunity, and we did that in section 1 when we did our setup. So we want !Mona pattern create. We'll use Mona a fair amount in this class as we do the exploit development. It has commands for a lot of useful tasks that make exploit development a bit easier. So we want to tell it to create a 1100 character pattern. So we're going to replace that 1100 A's with this pattern that is going to allow us to see where our save return pointer overwrite is in just one step instead of having to break it down into multiple steps like I showed you in the previous video. So I'll just paste that in. So Mona pattern underscore create and 1100. And since I set up the logs when I was doing this setup, it does log it to clogs war-ftpd pattern.txt, so it's clogs and then the name of the program it's attached to, and whatever the command is. So if I go to the desktop, not the desktop, that's where everything else is, clogs war-ftpd and then pattern.txt. There's our cyclic pattern that's 1100 characters long. So I'm going to copy this and move back over to my Kali VM. And I'm going to use nano and edit this warftpscale.py. And I'm just going to comment out buffer equals a times 1100. So that'll be a hash in Python. Then I'll recreate buffer. You could also just get rid of that line entirely or delete the a times 1100 and then redeclare it. But this is nice because we can see each step as we move through it. So it'll be nice to remember what we did, because I am going to have you do an exercise where you do it this yourself. So it'll be nice to have all the steps. Alright, so I'm going to say buffer equals open quotations and then paste in that 1100 characters of the cyclic pattern. And don't forget the close quotations at the end. Whoops. Mine ended up on a second line. That's no good. So it should light up green in nano. Alright, so instead of 1100 A's, now we're going to still send it 1100 characters. So the length should be the same. But now we have our little cyclic pattern. You can kind of see how it works. Big A, little a, 0, big A, little a, 1, so on and so forth. We get a little B and a little C. So you can see it could be pretty long before it has to loop around. So go ahead and save that. That's the only change we're going to make here. We're just redeclaring the buffer variable to be our cyclic pattern so we can crash it again. So make sure we are running over here in immunity. We are indeed running. So we should be good to go. So over at Kali, let's run it again. Get the same output here. So everything as expected here. It said, hi, I'm the WarFTP server. Please enter your username. Please enter your password. So we do, or the script does rather. So if we come back over here, we get access violation when executing, this time not 41, 41, 41, 41, since we didn't send it a long string of A's, we sent it our pattern. So instead we get 32, 71, 41, 31, and it's here in EIP as well. We can also see parts of our pattern in ESP, EVP, and EDI. Those were covered in A's last time, so that is to be expected. So what we can do, we have a couple options just to see what is in EIP. We could just do !Mona pattern underscore offset and then give it 32, 71, 41, 31. And it says that that piece of the pattern is at position 485, so it's 485 bytes into our attack string. But remember that, go back to the CPU view, we also have these registers that have been overwritten with part of the pattern. And I mentioned that that might be useful as a place to put our shellcode. So we can actually just do one step that will allow us to see all of the places that the pattern shows up in memory. So we can do Mona find MSP, so that's find Metasploit pattern. This cyclic pattern is part of the Metasploit framework. You can also use Metasploit to create it directly on Kali, but I typically use Mona for these sorts of things. Alright, so we can do a Mona find MSP, and we do have to crash it with the cyclic pattern in order for this to work, so we do need to have our cyclic pattern in memory. Otherwise it won't find it, because it's specifically looking for parts of this pattern in different formats. So let's do !Mona find MSP. And it's going to take a little bit here. You'll see it says searching down at the bottom. It is searching through all of memory for parts of that pattern. It will just take a minute or two for it to finish. So this will again give us the location of EIP, but it'll also find what's in our registers and any other place that happens to be overwritten as well. So let's see what it comes up with. Alright, now it's done. So we can take a look again at the output. So if we go to C logs war-ftpd, this one's called find MSP, so the files are named after whatever we told it to do. So here at the top we have all of the loaded modules for this one. So these are, you see some Windows DLLs that are loaded, and we also see WarFTP itself should be here somewhere. Like here's WarFTPD executable. It looks like it also has a DLL of its very own. And you see information about them, like their base, the size of them, whether they're rebased or not. So that basically just means whether or not they can move. You see one of them is rebased. And things being in the same place every time certainly makes exploits more stable. I'd be able to use them on other platforms, for instance, or at the very least on other Windows XP Service Pack 3 systems. So we generally like to look for things that don't move or don't move very often. And safe SEH, we will look at structured exception handlers, or SEH, in a later portion of this exploit development section, but they're not really relevant now. Notice that a couple of them do have safe SEH as false. That will certainly come into play. Address space layout randomization, or ASLR, that's false for all of them. That didn't come in Windows until Windows Vista. That said, It isn't a requirement that you use ASLR on your programs, and certainly legacy programs like this wouldn't have it enabled. So ASLR, or address space layout randomization, is another thing that makes things move. Anything that does have ASLR enabled on an operating system that does support it, so Vista or later, then it would, when you reboot, all of those DLLs, all those programs would be loaded at a different space in memory. If you continue with exploit development, you'll see ways to bypass ASLR. It is certainly relevant these days, but again, with this example and anything we're going to do in this class, we won't see that. If you take an exploit development class, I'm sure that will be covered. It's certainly covered in mine, but for now it's not relevant. Likewise, no execution. We don't have to worry about that here. So data execution prevention basically, again, is a way to stop exploits from working. So it's like, oh, we're executing code off the stack. Why are you executing code off the stack? You shouldn't be executing off the stack. The stack's just supposed to be like local information. It shouldn't be executing. So someone got the bright idea, well, let's just mark sections of memory that aren't supposed to be executed as not executable, and then people can't just put their shellcode there and execute it. So again, if you take an exploit development class, I'm sure you'll spend lots of time looking at different ways to bypass no execution, but we don't have to worry about it here. We don't have an X on. And it also says, are they operating system DLLs? And that's true of everything that is not WarFTP itself or any of its DLLs. So operating system DLLs are probably going to change among service packs, or could even change just among a few updates. And certainly among different Windows versions, they're probably going to change. Not necessarily are they going to change. There are some instances of DLLs that don't change that often. In my experience, MSV CRT is a good operating system DLL that you can use. It doesn't change very much in the history of Windows, whereas something like User 32 or System 32 does have a lot of changes. It's bigger, a lot more going on. So if I have to use an operating system DLL, I usually go for that MSV CRT.dll, but just for this basic example, really any of the operating system DLLs will work just fine. We're working with this specific platform, but we would like, as exploit developers, to make our exploits as universal as possible. And so my first thing is I try and go for WarFTPD itself or any of its DLLs, and if not, then MSV CRT if it's there. So we'll see that a bit later on. Alright, then the actual meat of FindMSP, the program, looking for our pattern. So it found quite a few parts of the pattern, but in particular I'm interested in the registers at this point. So EIP, again, it found its offset is 485, and it did find those other three registers, ESP, EDI, and EBP, all contain part of the pattern as well. So ESP is at offset 493, and afterwards it has the length of 607 bytes. So if we put our shellcode in ESP, we have 607 bytes for shellcode. More space means we can use more advanced shellcode. Certainly helpful. Let's see, EDI is at 749, and its length is 351, so not nearly as long there. EBP is at 581, and its length is 519. So EBP has almost as much space as ESP. Chances are we could probably use EBP just fine, but let's go ahead and grab ESP. It does have the longest length, and as we'll see, it'll make something interesting happen that I think is worth seeing, particularly if you're going to continue in exploit development. So I will choose ESP. That's where we're going to put our shellcode. So its offset is 493, and that has length 607. I'll just go ahead and copy this out. Oops. Find MSP, and untitled is what I want. So just copy this for reference. So offset is 493 and length is 607, and I'll also just put the EIP is at offset 485. So we found that with find MSP as well as with the pattern underscore offset that just finds EIP. So that means our save return pointer overwrite is going to be 485 bytes in. And then it looks like, so save return pointer is 4 bytes, so that'll get us to offset 489. But then ESP is at 493. So if we remember our picture from the beginning of exploit development, it said that our saved return pointer was right on top of ESP. So why are we 4 bytes off? That's kind of confusing. Well, sometimes the picture is not completely exact. What's happening here is the calling convention. There's different calling conventions, different compilers that you use, different platforms. They have different ways of dealing with things. There's certainly no hard and fast rules that this has to be done this way. So basically the arguments, so there's one 4-byte argument between EIP's overwrite and ESP, so there's 4 extra bytes that basically get stripped off when our whatever function we called returns. So there's just 4 extra bytes there. So nothing to worry about. It just makes our picture a little bit inexact in this case. But this is going to be taken care of automatically. We don't have to worry about ripping off extra arguments or anything. When it compiles, it takes care of all that automatically. We just need to know ESP is at 493, EIP is at 485. So we'll just take that into account when we build our attack string. So next thing we need to do, of course, is verify that this is all true. As you become more familiar with exploit development, you may skip that part, but I encourage you to always verify everything, because as soon as you stop, at least in my experience, that's when you start making mistakes, and we'd rather catch them now than way down the line when everything just stops working and you can't figure out why. Alright, so now let's verify those offsets. So let's go ahead and restart our FTP while we're here. Get that error, so let's remember to get rid of that FTP daemon.dat. So delete that. Again, if that doesn't, you don't get that error, you don't need to do that. So let's restart again. Next time I'll just remember to do that. Play. Lightning bolt. We're running. Alright, so let's come over to Kali again and open up our war FTP scale.py. Again, let's comment out buffer equals our pattern and recreate buffer and set it equal to, let's say, A times 485. Remember that that is our offset to EIP. So plus B times 4, so that should be 4 bytes for EIP. Remember there were 4 extra bytes for the calling convention for some argument that will be ripped off when program returns. So C times 4 for that argument. And then I'm not very good at arithmetic, so typically what I do is do buffer plus equals, so that's going to append to buffer. So I want D times 1100 minus the length, so len of buffer. So buffer's going to be 485 plus 4 plus 4. So we want the total string length to be 1100, and you don't necessarily have to have it be just as long. I generally, once I find something that does work, I stick to it. Why, add more possibilities of things changing. So I found 1100 worked. So you might have a question, how did we know 1100 characters worked? And that was absolutely a good question. We will in the absolute next, the next one. Our next example, we will look at something called fuzzing that will allow us to find crashes in the first place. But for this one, kind of like when we did our MSO 8067, when we first learned Metasploit, I said, just believe me that this vulnerability is there. And sure enough, we found it using vulnerability scanners, using the check function, and other methods that we used for vulnerability discovery. It was indeed there. Same thing here. I'm just telling you, 1100 characters does it, and we'll stick with that. Again, we will do fuzzing next and see finding a crash in the first place. Alright, so we still get the length 1100, so we're just padding it out with D's. So what we expect to see is B times 4, so 42, 42, 42, 42 in EIP, and then we should see 4 bytes of padding, and then at ESP we should see the beginning of our Ds, and again that's where we've chosen to put our shellcode. We have 607 characters to work with, so some of this 1,100 characters is not showing up. Or maybe it is. Maybe that's what's left is 607. See, I'm not very good at arithmetic. Yeah, that looks about right. Yeah, 607. So it looks like, yeah. Okay. This is why I just let it do the arithmetic for me. My arithmetic, again, is not that great. So that's the only change we need to make there. Make sure we do plus equals here in the second line. It is going to append. If we just do an equals, all you'll get is some D's, and it probably won't crash at all. Alright, now go ahead and run it. Again, this is just verifying our offsets, so hop back over to XP. And sure enough, we get access violation when executing 42, 42, 42, 42. We come to our registers, we see it. And we should automatically be following ESP in the stack, but we can right-click on a register and say follow in stack. And that should be the beginning of our Ds. So if we go up one, sure enough, here's our Cs, here's our Bs. So ESP is pointing at the beginning of our Ds. So if we put our shellcode there, it will, if we can get to ESP, of course, it will send us to the beginning of those Ds or our shellcode, and we can execute from there. We don't have data execution prevention on. We can execute off the stack just fine. So of course our next question is, how do we get to ESP? I got a little bit ahead of myself there. I'm like, oh, we can just go to ESP, but how do we get to ESP? Well, can we just hardcode the address in? Generally that's a pretty bad idea. It may move around, particularly between platforms. It's not always going to be in the same place. So anything that we hardcode like that may possibly move will make our exploit more unstable. We like it to be as universal and stable as possible. So that's generally a bad idea. Plus with this one we have another problem. Looks like ESP is at 00AFFD48. 00 is the null byte, and it turns out that in many cases the null byte is a bad character. It does represent the termination of a string, so if what you're working with is being used as a string by the program, so if it is calculating that to be a string, if it sees a null byte, it will say, okay, that's the end of the string, and everything that comes after will just be dropped off. So since our EIP overwrite is 485 bytes in, then that null byte would be at the end when we turn it into little endian. So everything after EIP would disappear, so all of our nice Ds that we're going to use for shellcode wouldn't be there anymore, so we actually don't have the option to hardcode this in anyways. Again, you're kind of taking my word for it that null byte is a bad character. It isn't always a bad character, not necessarily. You're always going to have a string. In this case, since it's the username, chances are it's going to be a string, but it's certainly possible that you'll run into exploits where it's not a string and the null byte will be just fine, or you may find some instances where you are forced to use a null byte and then you just lose everything after it, and hopefully you're still able to exploit it. You'll see lots of things if you continue in exploit development, but it is a bad character here. There's actually a couple more bad characters. So the bad characters for this one are null, 0A, and 0D, which are part of our enter, so our \r and \n. And then finally there is a fourth one. I was a bit confused when I first saw this one. 40 in hex is the @ symbol. If you look at man ASCII, you can see that. It's like, why the @ symbol? But as it turns out, since this is a username in FTP, the actual specification for it is username @server. So if I have an @ symbol in my username, it gets a little confused because it's like, okay, this is a server, but then there's an @ in there. So it's just part of the specification. I mean, that's really the key to bad characters, is you have to follow the specification for whatever protocol you're using and however it's being interpreted by the underlying program. So your bad characters are mainly going to vary based on what it expects to see, what it's capable of processing. So in this case, 40 is also a bad character because it is an FTP username. So, I mean, 0, 0, and 0A, 0D are pretty common. The 40, I see that a bit less. Usually an @ symbol is fine, but in this case it's not. Alright, so if we can't just hard code in our ESP is where to jump to, how are we going to get there? Well, I guess I kind of gave it away. We can jump there. So if we don't know much assembly, we may not be aware of it, but there is a command called JMP, short for jump. There's also call, which pretty much does the same thing, at least for our purposes. But Mona makes it pretty simple. We can just do a Mona. So if we do Mona JMP, that will find all the jumps and the equivalents as well. So calls, you could also do like, what can we do? We could do push ESP, so push ESP onto the stack and then return, which return will grab whatever the top of the stack is and then return to it or send execution to it. So we could just do Mona jump -R for the register, and in our case we want to get to ESP. We can also tell it to automatically delete any bad characters. We could also do this manually on site. Whoops. But let's just go ahead and tell it to take the bad characters out. So it'll automatically throw out any pointers that have a bad character in them. So not -B, -CPB rather. I always get that wrong. I don't know why. I always want to say CBP. But it's CPB, so bad is last, to tell it to get rid of the bad characters. So Mona jump JMP -R for the register, ESP in our case, and -CPB, and then our bad characters we want to avoid. So we put those down here at the bottom. Let that execute. So it's going to take a minute because it is searching through all of our loaded modules for jump ESPs and equivalents. That was pretty fast. So if we come over here to clogs war-ftpd, now we have jump.txt. See our modules up here at the top again. So here are all of our pointers. So we have jump ESPs, call ESPs, push ESPs, and then return. So it finds the equivalents as well, and it did automatically take out all of our bad characters, so technically we can use anything on this list. Again, I like to, just for portability's sake, if I can, use the war FTP module itself or some of its DLLs. It only has one DLL, this mfc42.dll. I'm not going to be able to use anything in war FTP itself because it is loaded with a null byte, so every pointer in there is going to have a null byte in it, which we want to avoid, so everything got thrown out there. It looks like our MFC, it doesn't seem like they're in there anywhere, so it doesn't look like there's a jump ESP equivalent in there, at least not one that doesn't have a bad character. So let's see. It doesn't have a null byte. Maybe it does. It doesn't look like it, no. But for whatever reason, they're not in there. So what we can do is choose another one. Again, in this case, you can use anything on this list. I like to use the MSV CRT. So here's MSV CRT DLL right here. So I'll just grab this one. So it's a push ESP and then a return. So it's an equivalent to jump ESP that Mona found. So again, you can use anything on this list as long as you automatically filter out the bad characters. You don't necessarily have to do the same one that I do. I'll just copy this and put it in my little notepad. Alright, so let's go ahead and restart. It is still crashed. So if we come over to immunity, let's get rid of that ftp.dat or ftpdaemon.dat. And then if we go to debug and restart, should open up by itself now. Sure enough, it does. Put the lightning bolt. And if we come over to our Kali, Now what I want to do, instead of b times 4 here, I'm going to put my jump ESP equivalent. I just pasted it in there for reference. I need to put it in little Endian format and tell Python that it's hex. So I need the 59 first, so again, byte by byte, turn it around. So 59 first, then 54, then C3, and then 77. And if yours is different, just make sure it's in little Endian format. So flip it around byte by byte, and put that in the place of our EIP overwrite. So in the place of our 42s or our b times 4. That's the only change we need to make right now. So let's go ahead and save this. And one more thing before we run it, I want to, like we did in the Linux example, actually set a breakpoint. So what we can do for that is just say BP for breakpoint, and then paste in. That didn't work out too well. Paste in that address. So BP and then alright, that's still not working. One more time. Edit, copy. Really? Okay. Alright, so I'll just write it in, because for whatever reason Immunity doesn't want to take it from me. Alright, so let's make this smaller so I can see it. 77C3 5459. 77C3 5459. Alright, so we're going to set a breakpoint there and hit enter. And we can see our breakpoints if we go to view and then breakpoints. So there's the address, the module, MSVCRT, it's always active, and it is a push ESP. Remember, this one is a push ESP and then return. It's actually 2 commands to do the equivalent of jump ESP. Alright, so let's go ahead and run it. So everything is as expected over here on Kali. If we hop back over to XP, we are paused, but we don't have a crash. If we look at EIP, it is pointing to our 77C3 5459 in my case, so in MSVCRT. So we are at a breakpoint. If we look at the CPU, we do see our push ESP followed by a return. So we could let it play, or what we can do is we can hit F7. If you're on a Mac, you may have to hit function F7, and that will just execute one instruction at a time. So if I do F7, do push ESP, we take a look at our stack, we now have ESP pushed onto the stack, and then we return, so that's going to take that address and then try and execute what's there. So we do that return. So again, let's do function F7 if you're on a Mac, just F7 on Windows. And that indeed does redirect us to the beginning of our Ds. If we go up any, it tries to take those Ds as it grabbed that null in front of it, and now it thinks that that's another command. But so it takes us to ESP, so the beginning of our Ds. So now, of course, we need to replace our Ds with something useful. It looks like 44 in hex is just increment ESP. So we see a long list of increment ESP, so it's not going to be particularly useful in terms of shellcode. So certainly we can use MSF Venom and take advantage of that Metasploit payload system and create some shellcode that'll be more useful for us. Okay, so now we need to create some shellcode. So let's start by restarting, since we're here. Delete this file and restart. Put it online. Let's reset our breakpoint, make sure it's set. Okay, so let's create some shellcode. Pop back over to Kali, and we are going to use MSF Venom. We can use any payload that we want for Windows. I like Windows shell underscore reverse TCP or underscore bind TCP. So it is going to be inline, so we don't have to use a Metasploit handler. We can just use netcat, since we don't have to deal with the staged payload. So let's do, yeah, bind TCP works. Okay, so then we don't actually have to set any options. If we do a -O, it'll show us the options, but we can just let it do the default port of 4444 if we like. And we do need to give it the bad characters. That's going to be -B. And our bad characters, we do need to tell it the space as well. We have 607 characters to work with. Remember, we found that in Mona Find MSP. So we need -B and our list of bad characters, which I gave you, and -S 607. You can also do the format as Pi to have it automatically put it out in Python format, so we don't have to worry about formatting it. Alright, that looks good to go. Let that generate. It should be encoded, so it will need to decode itself first thing before it actually runs, because chances are some of those opcodes that we said are bad characters will be needed. So it did encode it with Shellcode, and it is size 368, so it does not take up the entire 607 characters. So we will need to pad it accordingly. So I'll just copy this and open up my warftpscale.py. Above buffer, I'm going to paste this in, and it's called buff. Since it already is put in Python format, I can just drop it in. And then right after my 4 C's of padding, before I put in my D's, I'll just put buff right there. So buff again was, how big? 368. So we will leave our D's in. So again, we have it as length of buffer. So just putting in buff here will make it automatically adjust how many padding D's it puts in. So I think that makes life a little bit easier. We don't have to do the math. Alright, so this should be good to go. You may find that it is in fact not good to go, but it should be, theoretically. We've done everything correctly. So let's go ahead and run it. We do hit our breakpoint, so everything's good there. So we can do our F7, F7, and we should get to the beginning of our shellcode. So D9, EB, BD, A6. If we look here, D9, EB, BD, A6. So yes, that seems to have gotten us right to the beginning of our shellcode. So everything should be awesome, and it should decode itself into its original format, take it out of Shellcode, and then we should be able to execute it. Don't worry if your shellcode is somewhat different than mine. Shellcode is polymorphic, so it's not going to be the exact same characters, so you need not worry entirely about that. Alright, so if we just let it run, it says it gets an access violation when writing to 00000001, and it's paused, so it did crash, and it looks like we're actually still in, or near the beginning of the shellcode. We haven't gone too far. Well, let's see. Since it crashed, my guess would be we actually don't have our listener, but we can try. With netstat, A&O, and that'll tell us all our listening ports. 4444 TCP is not there, so this did not work. So something went wrong. Well, what went wrong, and how can we fix it? So this is going to be something that is going to come up, Not necessarily this particular situation, but there will be times if you just follow the script with exploit development, something won't work, and you can either, throw up your hands and give up, or you can try and debug it and see if you can figure out what's wrong. So that's why I like to start with an example like this, because it should be, oh, we're done, hooray. But in this case, something went wrong, and we are going to have to fix it, and I won't always be here to help. So, let's go ahead and restart, see if we can step through this and figure out what's going on. So, let's get rid of our extraneous file. Again, you don't need to do that if yours doesn't crash. Let's restart. Put it online. Reset our breakpoint. Make sure it's set. Alright, let's run it again. We definitely want that breakpoint because we are going to see what's going on with the shellcode. Run it again. Breakpoint, awesome. Let's do our F7s to get to the shellcode. Alright, so remember we are encoded, so it does have to decode itself. So my guess would be something is going wrong in the decoding because we're getting a crash. So if just one byte goes off, then it won't work. So let's look at what's happening here. It's actually this third instruction down that's our problem in this case. It's FST-ENV, and even if you are familiar with assembly, you may not be familiar with this particular instruction. What this is doing, well, it's in the process of trying to find itself in memory so it can decode itself with our decoder, so it's trying to basically find out where it is so it can decode the shellcode. But what this particular instruction does is it writes, in this case, a 28-byte structure to the stack, starting at ESP minus C. So 9, 10 is A, 11 is B, 12 is C, so ESP minus 12. So it's trying to write, so 12 bytes above ESP, because again the stack grows to lower memory addresses. It's trying to write 28 bytes. So it has 28 bytes to write, and it only has 12 bytes before it hits ESP. So what might that do to our shellcode that's sitting at ESP? Oddly enough, this particular setup with Shellcode sitting at ESP will actually, I guess, buffer overflow into our shellcode if you think about it. So it basically is only giving itself 12 bytes to work with. And it's using ESP as its base register. So, again, if we do F7s to get to that one. Now watch our stack right here. So our stack is the beginning of our shellcode at ESP. So if we execute that FST-ENV instruction, look at the first few bytes. So do our F7. Sure enough, the first few bytes of our shellcode get corrupted. Well, that's no good, is it? That's no good at all. So my guess is our decoder never finishes because it gets corrupted in the process of trying to set itself up. So that's a little bit unfortunate. It's just the way the decoder for Shellcode works. But it's something we can certainly deal with. Once we have jumped to ESP and we've gotten to the beginning of our shellcode, there's really nothing to say we couldn't move ESP somewhere else. Our Shellcode decoder is going to use ESP as its base when it's trying to find itself, but it doesn't have to point at the beginning of the shellcode. So why don't we just move ESP? We can probably figure out how to do the assembly for that. It seems like it should at least fix this particular problem. So let's restart while we're here. Alright. Set our breakpoint as well. And what we're going to do is go to user share metasploit dash framework and tools. And I'm going to open up metasm underscore shell.rb. So this is a rather nice tool that allows us to create opcodes from assembly without having to compile everything with NASM and whatnot. So I think it's fairly useful to get our opcodes from our assembly. So we'll open that up. It is a Metasploit tool. And so we want to move ESP. I want to get it far, far away from my shellcode. So if I add to ESP, that'll move me down the stack, and chances are it will still be in our shellcode. So I would like to subtract from ESP. So sub is subtract. In Intel format, the destination comes first, so subtract from ESP, comma, the amount we'd like to subtract. Let's say, how about 1500 bytes? That's certainly more than we need, but let's get it far out of the way. Well, there's just one problem with this. It's got null bytes in it. Nulls are a bad character, so we can't use those. So we're gonna have to do something else. We could do, like, maybe subtract ESP. What if we did, like, 200? Still null bytes, so let's see, 50? That might work, but we have another option here. How about, what if we do a logical equivalent? What if we add to ESP, instead of 1500, negative 1500? So we do the equivalent of subtracting. That doesn't have any null bytes in it, so why don't we do that? Let's copy this. And I'll exit metasm, go back to my desktop, and open up my war FTP. And I just want to put this right before the shellcode starts, so right before we start decoding, I'll just move ESP out of the way. The shellcode will not be affected, and that should hopefully, when that FST-ENV occurs, they'll keep that structure away from our shellcode, since we've moved ESP out of the way. Oops, it already had quotations around it, so when I copied it, I already had quotations there, so I got double quotations, so I had to take those out. And it had buff equals empty string at the beginning of our shellcode. That's just how MSFNM put it out, so I could just put that there. So, again, this is not going to be necessary every time. This is just particular based on the fact that it used Shikata Ganai and it was sitting at ESP. So this is one particular instance of shellcode crashing that you may run into. It will happen other times if you use ESP. Certainly this could happen again, but it's not the only way shellcode can crash. Really what I'm trying to show you here is that you shouldn't just be afraid of, oh, all this hexadecimal stuff, I can't figure out what's going on. Actually, you know, if you just look through it and spend a lot of time Googling about the stuff you don't know, like FST-ENV. When I first ran into it, I was like, I have no idea what that is. And I had done some assembly before. It's, you know, not add, subtract, pop, push, move, ones you see all the time. So, I mean, I had to Google it, but, you know, just Googling it, you know, stepping through it and seeing that corruption, I was able to figure out what's going on. And you can too. So it may take some time and effort, but it shouldn't scare you. Alright, so let's, as I'm saying, you can definitely fix stuff. Maybe I should check and see whether it actually works. So let's go ahead and run it again. We hit our breakpoint over here. Let's do our F7s to get to the beginning of the shellcode. So FST-ENV is still there as just the fourth instruction instead of the third, because we have add ESP -5 DC, which one can only assume that's some sort of hexadecimal representation. Alright, so let's do an F7 of that. So here's ESP now, pointing at the beginning of our shellcode. Now if we do an F7, ESP moves, and now we're nowhere near our shellcode on our stack. So if we let it run now, see if it in fact fixed our problem. So I just hit run, or the play button, and it's now running, so it didn't crash. And if I take a look at netstat-ANO, sure enough, port 4444 TCP is now listening. So I can do a netcat 76, I think. 4. Sure enough, we have a shell. If you used a reverse payload instead, if you did like Windows shell _ reverse _ TCP for the inline reverse, you would need a netcat listener. You could do like interpreter reverse TCP, but then you'd need to set up multi-handler. So, I mean, you can use any Windows payload. It should be able to fit in 607 characters with only 4 bad characters, so it should be good to go there. So you're welcome to try a different payload if you like. So there is going to be an exercise, so you will have a chance to do another example in the next section. Alright, as usual, if you've ever seen any of my talks or classes, I've gone over time a little bit, so I don't have long. I just wanted to thank you guys for coming and let you know that the slides and the write-ups covers everything we covered today, as well as some additional exercises. So if you enjoyed this and you want to keep working on it, please do work through the additional exercises as well. Again, I hope you guys had a great time.